Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss kinetic theory of gases and pressure exerted by the ideal gas. Let's begin. Kinetic theory of an ideal gas. There are some assumptions or postulates regarding this. These postulates are: all gases consist of molecules. What are the nature of that molecules? The molecules of gas are all alike and molecules of different gases are different. Same gases, the molecules are alike and different gas molecules are different. And the molecules, the gas molecules are very small in size as compared to the distance between them. That is, the molecules are point masses. We said molecules are point masses. Therefore, the size of the molecules are very small as we compare the distance in between these two molecules. Next postulate: the molecules of gas can be regarded as perfectly elastic spheres. The molecules of gas, as we consider, we say that is the point masses, and that is perfectly elastic in sphere and negligible in size. As we discussed here, it has very small size and that point masses looks like perfectly elastic spheres. Next one: molecules are in constant random motions, means they have the velocities in all directions ranging from 0 to infinity. If we take the molecules inside a vessel, the molecules possess constant random motions throughout that of vessel, and the molecules have the velocities, that velocity range from 0 to infinity. Next one: molecules collide with each other and with the walls of the container or containing that vessel, and these collisions are perfectly elastic. Due to that of random motion inside that of container, they collide with each other and also with the wall of that container, and these type of collisions are perfectly elastic in nature. Next postulate: between two consecutive collisions, as there are collisions are occurred due to the random motion of that of molecules inside that of vessel. So between two consecutive collisions, a molecule moves along a straight line, and this path is called the free path. This path of the consecutive collisions where molecules move along a straight line is known as free path. And if we take the average of large number of such type of free paths, which is known as mean free path, free path, the path on which the molecules moves along that of straight line due to that of consecutive collisions, and the average of large number of such type of free path is known as mean free path. Next assumption or postulate: the collisions are almost instantaneous. Instantaneous in the sense the time during which the collisions takes place is negligible as we compare to the time taken by the molecules to travel the free path. Means if we take that is the collision between the two molecules, that is the path followed, which is known as the free path. That type of collision is very instantaneous. Instantaneous in the sense the time during each collision is negligible as we compare the distance travelled by that of molecules. Means distance travelled by that of molecules to travel that of free path. Next one: molecules do not exert any force of attraction or repulsion. Force of attraction or repulsion cannot exerted by these molecules to each other. Means that molecule can't attracted to this molecule, or that molecule can't attracted or repelled by that molecule. Means they don't exert any force of attraction or repulsion on each other. Whole of the molecular energy is kinetic. Whole of the molecular energy is kinetic. The total energy due to that of kinetic energy, means there will be no such effect of potential energy in case of ideal gas. The number of molecules of a gas per unit volume remains constant everywhere in that of container. If we take the term as number of molecules per unit volume, how much number of gas molecules within that of unit volume, that is always constant throughout that of whole container where gas is placed. These points are basic postulates or assumptions for kinetic theory of an ideal gas. By using these assumptions or postulates, we can derive how much amount of pressure is exerted by that of ideal gas. So, let us study it. Pressure exerted by an gas. Pressure exerted by an gas. Pressure exerted by a gas. That gas is an ideal gas. So, how or what we said that the pressure is exerted by that of gas? Means when certain mass of a perfect gas is taken in a vessel, the molecules of gas are in random motion. They collide with one another and with the wall of the container. As the molecules of the gas strike against the wall of the vessel, they exert force on that of wall. This force per unit area exerted by the molecules of the gas on the surface is called pressure exerted by gas. Means force per unit area, exerted by the molecules of gas on the surface of that container or vessel is known as the pressure exerted by the gas. Let me calculate. Here we consider a perfect gas. Or ideal gas. Enclosed in a cubical vessel. Perfect gas enclosed in a cubical vessel. Let us draw that of cubical vessel here. That cubical vessel having each side will be small l. This is x axis, that is y axis, that one with the z axis, named as A, B, C. This is the origin O. This is D, G, D, E, F. And the side of that of cubical vessel is L. L be the size L, and these walls are perfectly elastic. Cubical vessel sides is equal to L. The walls are perfectly elastic in nature. In that of vessel, we consider perfect gas or ideal gas. Let the sides of the cube represents mutual perpendicular axis as x axis, y axis and z axis. This is the origin. Here we take the perfect gas or ideal gas within that of closed vessel. Let the total number of gas molecules in that of vessel. Let the total number of gas molecules in the vessel, let small n, with the total number of gas molecules inside that of vessel, and the mass of each molecule, let small m, mass of each molecule, and the length of each side of the cube, length of each side of cube, that is small l, that is the each side of that of vessel, and volume of the cube, volume of the cube, that is V, which is cube of that length, L cube. Let we consider, let C1, C2, C3, Cn be the velocities of molecules first, second, third, nth respectively. Means first molecule of the velocity c1, second molecule possess the velocity c2, like that. Since there are n number of molecules, each molecules corresponds to particular velocities. And let U1, V1 and W1, U1, V1 and W1 are the components of the velocity c1 along x, y and z axis respectively. Means if we take the velocity c1 here, so the x component of that of velocity c1 is u1, the y component of that of velocity c1 is v1, and the z component of that of velocity c1 be the w1. Similarly, u2, v2 and w2 are the components of the velocity c2 along x, y, z axis respectively. Okay, like all these things are happened here. Like un, vn and wn, velocity Cn along these axes respectively. Then according to the vector rule, so c1 square, this is the resultant velocity, that is u1 square v1 square plus w1 square, and c2 square u2 square v2 square w2 square, c3 square u3 square v3 square w3 square, up to which Cn numbers, Cn square is equal to un square vn square plus wn square. Here let me consider one molecule that moving with the velocity c1. Consider one molecule, first molecule with velocity c1. Let this molecule is moving along the x-axis. Let this molecule is moving along x-axis with velocity u1. So the initial momentum of the molecule, for the initial momentum of the molecule, that is mass into velocity, that is mass velocity u1. The molecules strike the face, that molecule strike the face DFED, DEFG, that face is struck by that gas molecule, that is a phase. This is a phase A, B, O, C. So here the molecule strikes the face DEFG. That means that face which is perpendicular to x-axis, DEFG, which is perpendicular to that of x-axis, which is perpendicular to x-axis and moves with the velocity, minus u1 after collision in opposite direction. Here in x direction that component has the velocity u1, but after colliding on that of face it reflects back, and that reflection, in case of that reflection, the molecule has the velocity minus u1. So here the final momentum of the molecule, therefore the final momentum of the molecule, that is mass into velocity, mass minus of u1. This is the initial momentum, that is the final momentum. Therefore, the change in linear momentum, what should be the change in linear momentum? So, we write here, therefore, change in linear momentum of the molecule, that is the final momentum minus initial momentum, final momentum minus initial momentum, final momentum minus mu1 minus of mu1, that is minus 2 mu1, that is change in linear momentum of that of molecule. Now, the molecule suffering reflection at that phase DEFG traverse a distance of L. When it reflects back by colliding on that of phase, it travels at a distance of L here, at the length of that of cube, and again strikes on that of phase OABC. It is reflected again with that of same speed and again traverse a distance of L before striking the face of DEFG. So, the total distance covered by that of molecule during one successive collision is equal to 2L. So, here we write the molecule suffering reflection at phase DEFG traverse a distance small l and strikes the face OABC. It is reflected again with same speed and again traverse a distance small l before striking the face DEFG. Therefore, the molecule again strike the face DEFG after covering a distance of 2L with the velocity u1. Therefore, time between two successive collisions is equal to, that is distance by velocity, is the time taken. Here the distance will be 2L and velocity will be u1. Let me take the time taken be t1, the time between two successive collision having that of velocity u1. Here, according to Newton's second law of motion, Newton's second law of motion, force exerted on first molecule due to the phase DEFG force exerted on first molecule due to phase D, E, F, G, that is the change in linear momentum, change in linear momentum to time. Here change in linear momentum, that is minus 2m u1, minus 2m u1 is the change in linear momentum, minus 2m u1, and the time taken is the t1 divided by t1. Now putting the value of t1 here, so minus 2m u1 divided by, that is 12 by u1, this is the value of t1. Again simplifying it, we get, that is minus m u1 square divided by L. This is the force exerted on first molecule due to the phase DEFG. Now from Newton's third law of motion, according to Newton's third law of motion, the action and reactions are equal and opposite. Hence, the action and reactions are equal and opposite. Hence, force exerted by first molecule on phase DEFG is given as F, that is force exerted on first molecule in that of x direction, that is x1, is equal to minus of m u1 square divided by L, that is f x1 is equal to m u1 square by L. Similarly, force exerted by second molecule on that of phase, similarly force exerted by second molecule on phase DEFG, that is F x2 m u2 by L. Force exerted by third molecule, for third molecule it is F x3, that is m u3 square divided by L, up to for nth molecule, that is F xn is equal to m un square divided by L. Therefore, the total force exerted by all molecules, total force exerted by all molecules on phase DEFG, that is f of x, total force exerted by all molecules on that of phase is equal to x1, x2, x3 up to xn. So f of x is equal to, that is m u1 square by L plus m u2 square by L plus m u3 square by L plus dot 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 m un square by L. Here taking m by L as common, or f of x is equal to taking m by L as common, so u1 square, u2 square, u3 square plus dot 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 un square. That value is what? That is the force exerted by all the molecules on that of phase DEFG. Now the pressure exerted by the gas, our aim is to calculate the pressure exerted by that of gas. So the pressure exerted by gas on that phase DEFG, that is pressure, that is P of x is equal to force by area, F of x by area A. As we know, pressure is equal to force per area. Force per area, that is area. Here area is the, for cube it will be L square. Now putting the value here, we have m by L cube, u1 square, u2 square, u3 square plus dot 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 un square. L cube, that is the volume, as L cube is equal to V, that is the volume of the cube. So m divided by V, that is u1 square, u2 square plus u3 square plus dot 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 un square is the pressure exerted by gas molecules on that of phase DEFG. Similarly, pressure exerted by the gas on phase ABFG, this is the phase ABFG, that is along that of y direction, that is ABFG, that portion. That phase, this is for ABFG, means y direction. Right here. Similarly, pressure exerted by gas on phase ABGF, that is perpendicular to y axis, that is P of y, we take that is m by V, that is V1 square, V2 square, V3 square plus dot 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 Vn square. Pressure exerted by gas on phase, pressure exerted by gas on phase BCDG, which is perpendicular to Z axis. Look at that figure. BCDG, that phase BCDG, which is perpendicular to that of Z direction. The pressure exerted, that is Py m by V as a W component, W1 square, W2 square, W3 square plus Wn square. This is, let I take equation number I, equation number II, and that one be the equation number III. From these three equations, let the total pressure be P. Let pressure exerted by gas is equal to P. Since the gas exerts pressure equal in all directions, since gas exerts the pressure which is equally in all directions, therefore P of x, P of y, P of z is equal to P, or P, the total pressure exerted by the gas, that is Px plus Py plus Pz divided by 3. From these three equations we take P is equal to m by 3V u1 square, u2 square, u3 square plus un square plus w1 square, w2 square, w3 square plus wn square plus, sorry, that is the v1 square, v2 square, v3 square, vn square. Third one, that is w1 square, w2 square, w3 square plus wn square. We know that u1 square, v1 square plus w1 square, that is c1 square. So combining these three, look here, the terms are how these terms are arranged. That is m by 3b u1 square, v1 square, w1 square plus u2 square, v2 square, w2 square plus let nth number of term, that is un square, vn square plus wn square, that is m by 3b. Here is the c1 square, c2 square plus cn square. Now multiplying and dividing n on both sides, that is m n 3b c1 square, c2 square cn square divided by n. That is m, small m, the mass of each gas molecule, n is the total number of gas molecules. Here we take that is the total mass of the gas molecule, that is capital M divided by 3b. And let we take, this is the c square, as m is equal to mn, that is the total mass of gas, and that term c, which is known as the root mean square velocity of the gas molecules, where c is equal to c1 square c2 square plus dot 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 cn square divided by n under root, that is the root mean square velocity of gas molecules. Here mass by volume, that is the density, that is 1 by 3 rho c square is the value of pressure. Here rho is equal to mass by volume, that is the density of gas. Density of gas. Here P is equal to that much. That is P is equal to this. This is how pressure exerted by the gas molecules. So, with the help of this video lecture, we understand the kinetic theory of gas, kinetic theory of an ideal gas, some assumptions or postulates, and then pressure exerted by a gas. We consider a perfect gas or an ideal gas inside that of closed vessel. This is the mathematical expression, pressure exerted by the gas, P is equal to 1/3 rho c square. What is rho and c? C with the root mean square velocity of gas molecules, rho is the density of gas. So, with this useful and informative notes, let me wind up this session. Thank you.